Okay, to pick up where we left off, or maybe a little after there, um, as I said, balancing is often possible by trial and error, but even then, there are a couple of basic rules that you should keep in mind just to avoid going around and around and around and never actually ending up with it getting balanced. And that would be, first of all, balance the elements in the most complicated compounds first. That is the compounds with the longest, most complicated formulas. And then leave any free elements for last. With our example of butane, we can try to balance that and see what we get. This is a relatively complicated one to balance. And so if you understand how to do this, you should have no problem doing anything that we'll encounter at this point in the course. So first of all, you want to start with the butane. You want to leave oxygen for last. Because C4H10 is the most complicated thing here. And remember, some elements are diatomic, so O2 is a molecule, but it is a free element. That's two oxygen atoms bonded to each other and not bonded to any other element. So the beauty there is that if you leave that for last, you can change oxygen without changing anything else. And that's why you want to leave free elements for last. We have in the C4H10, basically you can just go left to right, start with the carbon, why not? For the carbon, we have 4 carbons going in, and we only have 1 carbon going out. The only way that you can get 4 carbons out of carbon dioxide is, again, not by making it C4O2. That's a different compound, and I don't think it even exists. The only way you can get 4 carbons out of carbon dioxide is if you have 4 carbon dioxides. So put a 4 in front of it. You've changed the number of oxygens too, but that's okay. We're going to fix that later when we do that. So 4 carbons now lead to 4 carbons. So the carbons are balanced. Now you've got hydrogens. We've got 10 hydrogens going in, and the hydrogens coming out are part of H2O. We've only got 2 of them because for the moment we've only got 1 H2O. If you need a total of 10 hydrogen atoms and they come out in pairs in H2O, that implies that you're going to need 5 H2Os because 5 times 2 is 10. And that's how 5 H2Os will contain a total of 10 hydrogen atoms. Okay, so that's done. So far, so good. Now, you know there's got to be a catch. So let's look at the number of oxygens. We've got 2 oxygens going in. Coming out, we've got 4 carbon dioxides with 2 oxygens each. That is 8 oxygens. And I'm going to put this as OX just so you know that it's not a 0. 8 oxygens going there. And H2O has 1 oxygen each, and there are 5 of those. So that's 5 oxygens. That's 13 oxygens coming out. So we need 13 oxygens going in. The only catch is that 13 is an odd number, and the oxygens only come in pairs. Well, that's actually not as hard as it seems, because you could have, say, 13 halves as the coefficient for the oxygen. 13 halves times 2 would be 13. Or you could write it as 6.5 if you prefer. 6.5 times 2 would be 13. So at this point, the equation is balanced, and the only catch is that you're not allowed to have fractions in the balanced equation. So that means that that 6.5 or 13 halves has to become a whole number. you can make it a whole number by multiplying by 2, but then you throw everything out of balance because it is currently balanced. Well, what if you multiply this by 2 and multiply all the other coefficients by 2? So the 1 that's implied in front of the C4H10 becomes a 2. And the 13 halves in front of the O2 becomes 13. And the 4 in front of the CO2 becomes an 8. And the 5 in front of the H2O becomes a 10. Now it should still be balanced, and it's nothing but whole numbers. When you're done balancing the equation, or you think you're done, you should always check. Remember to count up all of the atoms on each of a given element on each side. There may be some cases like oxygen where the element is present in 2 different places, so don't forget that. So going in, we have 2 times 4 carbons. That is 2 butane molecules with 4 carbons each. That's a total of 8 carbons going in. And coming out, we have 8 CO2s with 1 carbon each. That is 8. So far, so good. Going in, now don't forget this either. You might look at this and say, oh, 10 hydrogens. Now remember, it's 2 times 10. 2 butanes with 10 hydrogens each. So that's 20 hydrogens going in. And coming out, we have 10 times 2, or 20. For the oxygens, we've got 13 O2 molecules. Uh-oh, wrong pencil. 13 O2 molecules, so for oxygen atoms, that's 13 times 2, or 26 going in. Coming out, we've got 8 times 2, which is 16, plus 10 times 1, which is 26. So that equation is balanced. One last thing to do. Sometimes when you're balancing, you end up using numbers that are bigger than they need to be. And you can still get an equation to balance that way. But officially, for the rules call for the equation to be balanced with the lowest whole number ratios of coefficients possible. So the last thing you should do is look through the coefficients and check for common factors. And if you look at the coefficients, 2, 13, 8, and 10, there are no common factors there. So this is the lowest whole number ratio of those coefficients possible. If this, say, were 2, 14, 8, and 10, then they would all be divisible by 2. And if they're all divisible by 2 or any other number, then you should do that. And you'll get lower whole numbers and it'll still be balanced. But in this case, this is the properly balanced equation, 2, 13, 8, and 10. Like I said, because of that odd number with the oxygen coming in pairs, this was a relatively difficult example. So if you understood that, then you're doing pretty well. Okay, that's a preview, sort of a look over balancing simple equations. Next, we look at chemical formulas from experimental data. This is about, say, chemical analyses that give you information which you can then use to find the formula of a chemical compound. We do stuff like this a lot in chemistry, particularly analytical chemistry. It's in order to find out what a compound is. You'll often do various chemical tests on it, and one test will tell you how much carbon you've got in the compound, and another test will tell you how much hydrogen you have in the compound, and so on and so forth. And you can put that information together to find out what the chemical formula is, because you know that those amounts of those elements all come from the same sample. So you can sort of compare them to each other and find out what the chemical formula is. So this is things like finding the chemical formula from percent composition data. Very often, from the kinds of data that we actually get from these experiments, what you end up with is the empirical formula for the compound. And if you want the actual molecular formula, well, empirical formula, remember, is all there is for ionic compounds. So if you're dealing with an ionic compound, the empirical formula is all you need. But for a lot of molecular compounds, the actual molecular formula will be some whole number multiple of the empirical formula. So you'll need other information in addition to things like mass percent type information. Okay. And the other information that you usually need is the molar mass. That can be found out from other tests. Okay, so a good example of that would be something like this. You have 500 grams of a compound and you decompose it, and what you get out is 200 grams of carbon, 33.3 grams of hydrogen, and 266.5 grams of oxygen. And so the question would be, what is its empirical formula? Pretty easy, actually. What you need to do is, first of all, find the number of moles of each element. Because what a chemical formula actually is just a relationship between the number of atoms of each element present in each unit of the compound, but that works on the level of moles too. If you have one molecule of H2O, you have 2 hydrogens and 1 oxygen. If you have a mole of H2O, then you have a total of 2 moles of hydrogen and 1 mole of oxygen. So those ratios are the same no matter how much of the compound you've got. So if you're given masses like you are here, then you can just use those masses to find numbers of moles. And then you can put those moles together to find your empirical formula. So we have 200 grams of carbon, and there's 1 mole of carbon for every 12 grams of carbon. And so that's 16.7 moles of carbon in this sample. We have moles of hydrogen. We had 33.3 grams of hydrogen. And there's 1 mole of hydrogen for every 1 gram of hydrogen. And that's 33.3 moles of hydrogen in this sample. And the moles of oxygen would be 266.5 grams of oxygen. And there's 1 mole of oxygen for every 16 grams of oxygen. And that gives us 16.7 moles of oxygen. Now, what you need for the empirical formula is just a formula that gives the relationship between the relative amounts of carbon, hydrogen, and oxygen. But you need that to be in whole numbers. So what you do is you take the number of moles of each element that are reported here and divide by the smallest of them. And here, 16.7 is tied for the smallest. And you end up with C, 1, H, 1.99, O, 1. When you're coming up with, when you come up with a number like 1.99, you can round that off to 2. And you don't have to write the 1s for the C and the O. So we end up with empirical formula CH2O. And it's really that simple. CH2O is the empirical formula. And it works the same for molecular or ionic compounds. And the molecular formula is actually a whole number multiple of the empirical formula. Remember, in the case of ionic compounds, the empirical formula is all there is. So if this is an ionic compound, you're done with the empirical formula. And I won't really try to trick you on that. I won't ask you to go on and find the molecular formula if it's an ionic compound. But if it's a molecular compound, and you should definitely suspect that it is, because it's made up of carbon, hydrogen, and oxygen, the fact that there are no metals present should tell you that it's not an ionic compound, and that would mean that it's a molecular compound, because that's the only alternative from what we've studied so far. So for the molecular formula, remember, it's going to be a whole number multiple of the empirical formula. And what you need is the molar mass. And what you do is take the ratio of the molar mass over the empirical formula mass, and that'll be equal to some whole number x, and you then multiply x by the empirical formula, and that's the molecular formula. Okay, so with the example above, we can say that, as we just found, has an empirical formula of CH2O. If that compound has a molar mass, which is also known, remember, as molecular weight, of 180 grams per mole, what is the molecular formula? Well, what we have to do is find the empirical formula mass. And that will be CH2O, so it's 1 times 12 plus 2 times 1 plus 1 times 16. And that's 30 grams per mole. Then you take your ratio of the bigger number over the smaller number, or the molar mass over the empirical formula mass. And it's 6. 180 divided by 30 is 6. So you multiply the subscripts in the empirical formula by 6. And lo and behold, it's our old friend glucose, C6H12O6. And that is your molecular formula. The same thing can be done with percent data. If you're given percentages instead of masses for each of the elements present, then all you have to do is assume that you have a 100-gram sample, and the percentages immediately become masses. So again, if you're given percentage data instead of masses, just assume that you have 100 grams of the sample, and then the percentages immediately become grams, and then proceed as above. Okay, there is a section on combustion analysis also. Combustion analysis is where you burn a sample in an environment with lots of oxygen present, and the products will be carbon dioxide and water vapor. And the basically the theory is, anyway, that all of the carbon in the sample becomes CO2, and all of the hydrogen in the sample becomes H2O. And if there's any remaining percentage that's unaccounted for, you forget the oxygen. Or sorry, I'm reading something else. If there's any unaccompanied percentage, you assume that that's oxygen, or any sort of unaccounted for percentage is what I was looking for. So any unaccounted for percentage is assumed to be oxygen. An example of this could take some space, so I'm going to go to the top of a new page. Combustion of a compound containing carbon, hydrogen, and oxygen. And a 10-gram sample of this compound produces 14.7 grams of CO2 and 6.04 grams of H2O. And so what is the empirical formula? First of all, I'm going to write a little note here. Don't forget the oxygen, because that's a pretty common thing to do in questions like this. So what we do is take the amounts that we're given, 14.7 grams of CO2, and we find out how many moles that is. Because there's because we know that there's 1 mole of carbon for every mole of CO2. So if you find out how many moles of CO2 you've got, you find out how many moles of carbon were in the original compound. Okay. And I'm going to write the 1/1 just to make it official. Notice that grams of carbon dioxide cancel and moles of carbon dioxide cancel, and we get moles of carbon. And so we have 0.334 moles of carbon. Then we have our 6.04 grams of H2O. There's 1 mole of H2O for every 18 grams of H2O. And in this case, we know that there are 2 moles of hydrogen for every mole of H2O. And that gives us 0.671 moles of hydrogen. And for the oxygen, we need the mass of oxygen. It didn't give us the mass of oxygen. So what we need to do is find the masses of carbon and hydrogen and subtract them from the mass of the sample. Okay, so for carbon, we've got 0.334 moles of carbon at 12 grams per mole. And that means for carbon, we've got 4.01 grams of carbon present. For hydrogen, we've got 0.671 moles of hydrogen, and there's 1 gram of hydrogen per mole of hydrogen, and that's 0.671 grams of hydrogen. Okay, so mass of oxygen is going to equal the sample mass, that's 10.0 grams, minus 4.01 minus 0.671. And that comes to 5.32 grams of oxygen. We also, for the formula, we need moles. We've got moles of carbon and moles of hydrogen. We now need moles of oxygen. We've got mass of oxygen, 5.32 grams. And we know there's 1 mole for every 16 grams of oxygen. And that's 0.332 moles of oxygen. Okay, so now we can come up with the empirical formula. In which we use moles of one element to moles of another. So we have carbon, 0.334 moles, hydrogen, 0.671 moles, and oxygen, 0.332 moles. And of course, we need whole numbers for these moles relative to each other in order to come up with a proper empirical formula. So you divide all of those moles by the smallest, which is 0.332. And we come out with C 1.01, H 2.02, O1. And again, when you come out with numbers that are that close to a whole number, just round them off. So that's CH2O, our old friend glucose, or at least that's what it will become once we find the molecular formula. So our empirical formula, again, is CH2O from the combustion data. Okay, so there we have another segment, and it's about 30 minutes, so I guess that's the end. Bye.